Welcome to my talk. I am RYC. Today I'm going to be talking about dynamical donuts. So we'll be talking about the dynamics of tori. If you remember, a torus is like a donut shape. Um, so that's what we're going to be talking about today. Now, I know that this is a recording of the talk. So in the original talk, I had some videos that I showed, which were great videos, but I don't own them. So I will reference in the description where you can go to look for some great videos showing the stuff that we're going to be talking about, but I will not be showing them during this recording. All right, so let's get to the talk. So what are we going to be talking about today? Today we are going to be talking about 3 different topics. We're going to be starting by talking about the translation torus, and we're going to talk about the dynamics on a translation torus, and we're going to prove what happens. And then what we'll do is we'll generalize these ideas to talk about the dynamics on different surfaces called translation surfaces and dilation surfaces. And finally, what we'll do is we'll talk about a specific case where we understand what happens with the dynamics in the case of dilation tori. And these get a lot more complicated than the torus that we'll start with, but they show some really, really cool behaviors. So let's start by talking about the typical torus. So what exactly is a torus? A torus is a square where we take the sides and we identify them according to translations. So, you'd have your square like this, and you'd take the left side and you'd identify it over to the right side. What I mean by identify is you just glue them together. And you take the top and you'd identify it to the bottom. So you kind of glue them together. And if you take the left and identify it to the right, you make a cylinder, and then you pull the ends of the cylinder around and glue them together to get a donut. Okay? And this donut shape is what we call a torus. And we call it a translation torus because we translated one side over to the other to identify them. We didn't like twist or stretch or shrink. We just pulled one over and glued it on. And so what are the questions that we can ask about a torus? Well, we can ask questions about its topology, like how many holes does it have? We can also ask questions about, say, its geometry, like what's the curvature of the surface? And finally, we can ask questions about dynamics. So dynamics are what we're interested in for this talk. And questions about dynamics look something like, if you start at a point and you start moving around, then what's going to happen in the long term? Where will you end up? Will you come back to where you started? Does something else happen? Can we answer questions about moving around on the surface? So this is what we're going to talk about. So let's start to understand the dynamics on a translation torus. Well, what do we mean when we say we want to move around? We start at some point and we start moving in a straight line. This is the natural straight line flow on a torus. So you start at some point and you start moving and moving, and eventually you hit the side. And when you hit the side, you come out the other side, moving in the same direction you were moving before. Okay? So that's what's going to happen. And flows on a torus like this are going to live in 2 very different dynamical worlds. So we'll see these 2 worlds, but let's start with the simple one. First of all, the flow could be periodic, which means that it came back to where it started. So let's see what happens in this case. We start here and we start moving. We start moving over here, and then we hit the blue side and we come back out the blue side, go through the red again, and we found that we came back to where we started, the black dot here. And so if we come back to where we started once, then we're going to keep following this path over and over and over again because we're still moving in the same direction. So we're going to keep tracing the same path over and over. We're never going to go anywhere else. And you can find that actually if you start at any point on this torus and you start moving in the same direction, then you're going to also come back to where you started. Okay? So this is what I mean when I say a periodic flow, a flow that periodically comes back to where it started. All right. So what happens when we fold this up and see what actually happens on a donut-looking torus? We get something that looks kind of like this. So you start at some point, you start wrapping around, but eventually you come back to where you started. Okay? And lots of interesting stuff can already happen with this. For example, if you make your slope shallow enough, then you can even do things like embed a trefoil knot into the torus, which is really, really cool. Um, but we are interested in when this happens, right? So we want to know what happens when we start moving in a direction. So for what directions is it the case that we're going to come back to where we started and have this periodic flow? Well, as it turns out, it's going to happen whenever the slope of our direction, so whenever the slope of our line is a rational number. So whenever we have a rational slope, then we're going to come back to where we started. So in this case that we've been showing, we had the slope m equals 2. And what that means is, whenever we move over by 1, we go up by 2. So you could imagine having your slope be any rational number. Whenever you move over by 1, you go up by p over q, where p and q are integers. Okay? So let's try to understand why this happens. Why is it that when we have a rational slope, we come back to where we started? Well, we can do a proof. So we'll start at some point x, y, and we're going to represent that point on the translation torus as a point in the unit square. So, you can imagine your point x, y as having an x coordinate and a y coordinate, and both those numbers are between 0 and 1. Okay? And we're going to flow with a slope m, which is equal to p over q, where p and q are integers. So m is going to be a rational number, it's in q. And after time t, so t is some amount of time, x is going to move by t units, while y is going to move by m times t units, right? Because we're moving at a slope of m, so for every 1 we move over, we move up by m. So after moving for time t, we're going to end up at the point x plus t, comma y plus mt. But we have to be careful because on a torus, whenever we get bigger than 1, we have to come back down to where we started at the bottom. And similarly, whenever, that is true for both the x coordinate and the y coordinate. So, on the torus, whenever we go up above 1 here, we need to come back down to 0. And similarly, whenever we go to the right of 1, we need to come back to the left. Okay? And how do we represent this? Well, you can imagine if you have a number like 1.1, then we need to bring it back down just to 0.1. So we're kind of cutting off that integer part of the number. The integer at the front of 1 needs to be chopped off and replaced by a 0. So in order to do this, we'll take our coordinates that we end up with, and we'll take the fractional part. Okay? So the fractional part says throw out whatever the integer is, just make it 0, and just leave what comes after the decimal sign. And we represent that by putting curly braces around the number. So we end up at this point, curly braces of x plus t, comma, curly braces of y plus mt. So we just took the fractional part of each of our coordinates. And that brings us back into the torus. And now we want to try to see if we ever come back to the point x, y. Okay. So let's try this time, t equals q. So let's see what happens. Well, first of all, how far is x going to move? Well, x is going to move by to x plus t, which is equal to x plus q, but q is an integer. So the fractional part of x plus q is just the fractional part of x, because q doesn't change anything that comes after the decimal sign, or the decimal point. Okay, so that's good. But what about y? Well, y plus m times t is equal to y plus m times q. But remember that m was equal to p over q. So we actually get that the q's cancel out, and we just get y plus p, because m times q is equal to p. But p is also an integer, so therefore y plus p has the same fractional part as y. Okay? So we flowed for time t equals q, and we came to the point x plus q, comma y plus p. But that's in fractional parts. And that point is exactly equal to the point xy that we started at, because y plus p is just y, and x plus q is just x. So we see that we came back to where we started. And since x and y were arbitrary, and our slope m was an arbitrary rational number, we have proved that if you start at any point and you move at a rational slope, then you come back to where you started. And when do you come back to where you started? Well, you come back to where you started after time q, where q is the denominator of your rational slope. And you can reduce it to see that, to see the minimum time that you come back to where you started. Okay? So this is kind of the idea for periodic flows. They happen whenever we have a rational slope. All right, but this begs the question, what happens, if we know what happens for rational slopes, what happens for irrational slopes? Okay, so now we could change our slope to square root of 2, and we know that square root of 2 is an irrational number. It can't be written as the fraction of two integers. Okay, so we start moving in this direction. We move over by 1, and we move up by square root of 2 every unit of time. And we want to know what happens as time goes on. Well, you can imagine we probably don't come back to where we started, because it was pretty essential that we flowed for time t equals q, where q is the denominator of our fraction. But even more interestingly than that, we actually shade in the entire torus. We don't just not come back to where we started, but we also go pretty much near any point in the torus at all. We don't actually hit every point, but we get arbitrarily close to any point. And so we call this a dense flow. The flow is dense, where dense means what we usually mean by dense in topology. What we mean is if you pick any point on the torus, then there's a sequence of points in our space so that those points are approaching that point on the torus. Okay? So there's a sequence of points on the flow which get closer and closer and closer to any point at all that you want on the torus as time goes on. So this is kind of crazy. It says as time goes on, eventually you'll get closer and closer and closer to any point in the torus at all. And this is super different behavior from what we had for the rational slope. For the rational slope, we barely went anywhere at all. We basically left most of the torus unfilled. But with an irrational slope, we found that we filled in almost everything, which is kind of crazy. So how do we prove something like this? Well, it's a little bit more in-depth of a proof than the proof for rational slopes, but if you focus on the picture, you might be able to see what's going on. Okay, so let's try to go through the proof. So first of all, we're going to start at this point xy. Okay, and what do we want to prove? We want to prove that if we flow with an irrational slope m, then if you pick any point at all vw, then eventually we're going to get within any error of vw. So we'll pick a point vw, we'll pick an error epsilon, and we want to know if we ever get within epsilon of vw. So you can imagine a little circle around vw with radius epsilon, and we want to know if our line ever intersects that circle. And if it does, then, well, we can make epsilon smaller and smaller, and we can say that over time our flow will keep getting closer and closer to vw. Okay? And it'll be true for any point, and it'll also be true for any starting point xy. Right? Now we'll see where this irrationality of m comes in handy here. It's very, very important at one particular step, so we'll see that. All right, so how are we actually going to do the proof? Well, what we're going to do is we're going to flow at first until x plus t. So, we're flowing for time t until x plus t is equal to v. So what does this mean? It means that we end up on the vertical line going through vw. So this vertical line going through vw, well, now we've matched up the v coordinate and the x coordinate, okay? So we've matched up those two coordinates, and that's good, because now if we can match up the y coordinate with the w coordinate, or if we can at least get them close, then we'll have gotten close to vw, right? So we've hit this line, and what we're going to do is we're going to take that line and we're going to split it up into lots of little boxes, and each box is going to have size epsilon. So remember, epsilon's our error, so if we split it up into all these little boxes, what we can do is we can think about, every time that we come back to our line as we move around and around and around, if we mark a point on that line, saying, I hit this point, I hit that point, I hit that point, we can pay attention to which box each point falls into, okay? So that's what we're going to do. We're going to think about this kind of meter stick, and we're going to keep flowing, and we're going to keep hitting this line over and over again. And every time we hit the line, we're going to mark a point in the relative box, right? So what's going to happen? Well, we're going to keep hitting the line over and over again. And eventually, we're going to hit the line so many times that we're going to make more marks on the line, more points on the line, than there are boxes. Because how many boxes are there? Well, each box is of size epsilon, and the line is of length 1. So there's about 1 over epsilon many boxes. So if you just keep hitting the line over and over again, then eventually you're going to get to a point where you have more than 1 over epsilon times that you hit the line. Okay? But now we can remember the pigeonhole principle. So if you remember the pigeonhole principle, it says that if you have k pigeons and n boxes, and k is bigger than n, then if you put all the pigeons into the boxes, some box must have more than one pigeon. Right? So this is kind of an obvious fact. It says that, if you have more things than you have spaces for things, then one of the spaces has to have more than one thing. Okay. Well, in this case, now we have more dots than we have boxes, right? So one of the boxes has to have 2 dots as time goes on. So eventually we're going to mark 2 points in the same box. So we can say that the n-1th time that we hit the box is one of these points, and the n-2th time that we hit the box is another point. And you can represent these points, these y-coordinates of these points by these values. The x-coordinate is just going to be v. Okay. So what's going to happen? Well, because they're in the same box, that means they're less than epsilon apart, because the boxes are only size epsilon. But really, really importantly, these points are also not going to be the same point. Okay? So if they were the same point, then what we could do is we could subtract these two numbers, and we would just get 0, right? Because they're the same point, so the fractional parts are, they're the same point, so you subtract them and you get 0. Okay. But then we see that the fractional part of m times n2 minus m times n1 is equal to 0, which means that m n2 minus m n1 is equal to an integer. But then we can divide by n2 minus n1, and we'll get that m is equal to an integer divided by n2 minus n1, which is another integer. But that's a rational number. So because m is irrational, this can't possibly happen. The 2 points can never coincide. Okay? This is also why we couldn't have ever come back to where we started. You can do a similar argument to show that m, therefore, would be rational if you did come back to where you started at some point. All right? So, you never come back to the same point twice, but you do end up having 2 points that are in the same box. So they're epsilon away from each other, but they're not 0 away from each other. Well, all right, now let's subtract the points. And we know that the difference is within epsilon of 0, right? But we know that it's not exactly 0. So if I take 2 times that, if I go around another n2 minus n1 times, then I'm going to be within epsilon of when I went around m times n2 minus n1 lines, m times n2 minus n1 times. And that's because the difference of these two is just m times n2 minus n1, which was less than epsilon. Okay? And I can keep doing this. So we can look at the picture down here now. I keep climbing up this ladder. So this is m times n2 minus n1. I climb up, climb up, climb up. And every time I climb up, I'm moving up by less than epsilon, right? So I kind of hit every box as I go up. I can never skip a box because then I would have skipped a gap of more than size epsilon. And eventually, as I keep climbing up, eventually I find a point where I kind of sandwich W in between 2 of these points, right? So you climb up, climb up, climb up, and eventually, W is somewhere on this axis, and we sandwich W in between 2 of these. But these 2 points were less than epsilon apart, and that means that one of the points, or both the points, are actually within epsilon of W, because W is in between them. And so this actually shows that the point that we came up with, which was at the k times n2 minus n1th time that we hit the line, is within epsilon of W. Okay. So what did we actually show there? We showed that eventually we hit this line so many times after k times n2 minus n1 times that we hit it just below V or just above V, just below W or just above W, and exactly on V, which means that we are within epsilon of V, comma W. So that shows that the irrational flow, this flow at an irrational slope, is going to be dense. Okay, so we have shown the flow for rational slopes, and we've shown the flow for irrational slopes. So now we fully understand the dynamics on a torus, which is great. Now, I think it's useful just to think about, we kind of shown what happens if you take the rational flow and you fold it up. So let's see what happens if we take the irrational flow and fold it up. And we get a picture that looks kind of like this. So what's happening here, you have this flow and it's moving around and it keeps kind of filling in its gaps that it had left unfilled before. So, you can see that this isn't the full flow, it's ended right here and it's going to keep going around and around and around, and it's going to keep filling in these gaps, getting more and more striped as time goes on. Okay. And if we looked at a picture of the finished flow, then we would essentially just see a shaded in torus. All right. So this is the dynamics on a translation torus. We now fully understand them. So what happens next? Well, what we can do next is we can generalize this idea. So let's start to talk about translation and dilation surfaces. All right. So what is a translation surface? A translation surface is just like a translation torus, except now instead of a square, we're going to use any polygon. So we'll start with a polygon, and we're going to identify pairs of sides by translations. So importantly, this means that your polygon has to have pairs of parallel congruent sides. So parallel because we need to be able to translate them, and congruent because they can't stretch or shrink, right? Okay, so if you have a polygon that has pairs of sides like that, then when you identify the pairs of sides and you kind of fold things up, you're going to get a resulting surface. It's going to have no curvature because it comes from a flat plane, except that it's going to have finitely many of these cone points. So a cone point is kind of like when you fold up all these vertices onto one point, or maybe a couple points. And when you fold them all up, all that angle kind of gets bunched together. So here, if you check out the surface, this surface comes from an octagon, and remember that the interior angles of an octagon sum to 1,080 degrees. But if you check, all these points are actually going to fold up onto one point. So you're going to have 1,080 degrees all around one vertex, which is kind of crazy. So you have this big floppy thing, and that's why we call it a cone point. Now, maybe we're used to thinking of cone points as points where there's too little angle. In this case, it has too much angle, but the idea is the same. Okay, so with this surface, for example, if you fold it up, what you'll see is you'll actually get a surface that looks like a chain link. So it's going to be a genus 2 surface. It'll have two holes, not quite a donut, but it'll look similar to a donut. How do you see something like this? What you can do is you can kind of fold the red side over on the red side, and then fold the green side over on the green side, and you'll get these two kind of holes left over, and then the holes will connect. Okay. So this is an example of a translation surface, and we can talk about the dynamics on a translation surface. So because there's no curvature, we still have a natural straight line flow, right? So we can still start at a point, and we still know what it means to move in a straight line. And moving in a straight line means we just move until we hit a wall, and then we go to the identified point. So, this flow will keep going like this, and it'll keep going. And we can ask the same questions we did for a torus. Do you ever come back to where you started? Do you maybe shade in the entire surface and have a dense flow? Maybe you do something else, like you only fill in part of the surface. And the celebrated theorem of Kirchhoff, Maser, and Smiley, which was only proved in 1986, so this is actually a very modern theorem, says that for any translation surface at all, no matter what it looks like, if you take the straight line flow in starting at any point at all, in almost any direction, then the flow is going to be dense. So this is kind of crazy. It says that the behavior that we observe for tori, which is that if you start at almost any direction, at any irrational direction, then you're going to get a dense flow. Okay, so importantly, what do I mean by almost any? Almost any here means that if you pick a direction at random uniformly, then you're going to have an 100% probability of that direction having a dense flow. So it's not always just going to be the rational slopes, it could be other things, but it will always be like the rational numbers where very, very, very few of the real numbers are rational. Very, very few of the possible directions will be directions where the flow is not dense. Okay, and then what happens in those directions that are not dense? Well, just like on the torus, you'll either come back to where you started or you'll do something else, but it won't be something too crazy. Okay? So how did Kirchhoff, Maser, and Smiley prove this theorem? Well, it's a far cry from the proof that we did for the torus. This is a very, very difficult theorem to prove. It requires math from various different areas of very theoretical work that's very modern. So for example, they used complex analysis and complex geometry to prove this. They used algebraic geometry, and they used the theory of ergodic theory. So these all kind of combined together in order to develop this really cool proof. So the proof looks something like this. Instead of thinking about just a single surface, you take all the possible translation surfaces and you put them together into a single space. Okay, and so what does it mean to move around in the space? Well, you take your translation surface and you kind of nudge it a little bit. So maybe you nudge this corner upward, and then that nudges this bottom corner downward because it has to still be a translation surface, but you can imagine how you'd kind of move things around in the space. Okay. This space is called the moduli space of translation surfaces. And once you have the moduli space of translation surfaces, we can think about a new flow, not the straight line flow on a single translation surface, but the flow on the moduli space of all translation surfaces. And what does this flow do? All it does is it takes your surface and it stretches it horizontally and it shrinks it vertically. Okay, so that's what the flow does. It's called the Teichmüller flow. And what Kirchhoff, Maser, and Smiley did was they proved that the Teichmüller flow has something called an invariant measure. And once you prove that, which is some complicated thing, you can actually carry that back over to each individual translation surface and say that on each translation surface, the straight line flow in almost any direction is dense. Okay? So this is what we can get from doing this crazy theory of moduli space. So this is really, really cool. Kirchhoff, Maser, and Smiley's proof actually inspired a lot of the work that was done by various researchers very recently, including Maryam Mirzakhani, who many of you might have heard was a Fields medalist, an Iranian woman who won the Fields Medal, and then unfortunately passed away due to breast cancer in, I believe, 2014. So, this theory kind of has a very exciting but also tumultuous history in terms of the mathematicians who have been working on it. But it's still a very kind of hot topic today of like, what can you do with these moduli spaces? All right, so we understand what happens on translation surfaces, even if the proof is way too complicated for us to talk about in this talk. And what can we actually do with these surfaces? So, they're kind of useful for a variety of things. They come up in a lot of contexts in physics, things like solid state mechanics and crystal lattices. Translation surfaces come up a lot, but I guess the two big applications that we see a lot are the rational billiards problem. So this is the problem where you have a table and you imagine playing billiards on the table. So you have a ball and it kind of bounces around on the table and you want to know what happens to that ball as time goes on. What does its trajectory look like? Does it come back to where it started? Does it fill in the whole surface? Does it fill in the whole table, I guess? Et cetera, et cetera. Okay? And if you imagine a billiards table where the angles are all rational multiples of pi in radians, or maybe they're rational numbers of degrees, then you can actually solve this problem of what happens to a ball on a billiards table using the theory of translation surfaces. So what you're going to do is you're going to take that billiards table and you're going to kind of unfold it like this, and you're going to unfold it over and over again until you get something that actually is just a translation surface. So what does that look like? You have this trajectory here, And when you would bounce off the wall, instead you just keep going through and you see that it's a reflection of what you would have done otherwise. So this is kind of this reflected version of the table. And then you can reflect again upward, and you'll find that you'll only need to reflect it out 4 times until you just get a translation surface. And we already proved what happens for translation tori, so now we can carry that back to a square billiards table, and we'll actually know that on a square billiards table, if you move at a rational slope, then you're periodic, and if you move at an irrational slope, then you're dense. Okay? So we've actually already handled the rational billiards problem on a square. Now, you could imagine more complicated tables, which are not realistic, but which also have rational angles like this, and you could use the theory of translation surfaces to understand them. We also have this problem of illuminating rooms. So, you imagine you have a room that has mirrors on all the walls, and you shoot a laser from some point. And your question is, does the laser hit every point in the room? Does every point in the room get illuminated? Well, it turns out that you can come up with rooms that don't have this property. So this is similar to the billiards problem where you have things bouncing off the walls. And there are some really, really interesting kind of examples where you have rooms that are unilluminable. So, I encourage you to check these out. But there's another really cool topic that's related to this, which, maybe you've seen Zach Starr's video on this. Maybe you've seen on YouTube Nils Berglund, his kind of animations that show this process happening, among with a lot of other really, really cool animations about dynamics. It's this idea of blocking sets. So imagine you're standing at one point in a room and somebody else is standing at another point in the room, and it's a square room with mirrors on all the sides, and they're trying to shoot you with a laser. Okay. So it seems like you can do nothing to escape because the laser is going to just bounce off the walls everywhere, and you're just going to get hit from all directions. But now what I'm going to do is I'm going to give you a finite number of pillars, and each pillar only has 0 thickness, but if a laser exactly hits that point, then it's going to get blocked by the pillar. And you have 0 thickness too, so it's okay, it's not like you're like a typical person, you kind of just occupy one point. Okay? And the question is, can you place pillars around the room in such a way that you will never get hit by the lasers? Well, this seems like it's impossible, right? Because the lasers are going to be bouncing all over the place. You only have finitely many pillars. Surely the laser is going to get through a gap and hit you. But as it turns out, you can do this with only finitely many pillars. In fact, you only need 16 pillars, and we know exactly the configuration of where they should go. So this is really, really wild. It's super surprising that this happens. I really encourage you looking up videos of like what this looks like. I can include, a reference to cool videos about this. But this theory of blocking sets, where you can put these pillars to stop the laser from hitting you, can be extended to more complicated sort of translation surface settings than just the torus, which is where we just solved the problem. Okay? So this is kind of a really cool topic in the vein of translation surfaces. All right, so let's move on now to dilation surfaces. We totally understand what happens with translation surfaces, or at least Kirchhoff, Mazur, and Smiley understand. So now the question is, can we generalize the idea even further? So what we're going to do this time is we're going to change how we identify the sides. So it's similar to translation surfaces, where we're going to start with a polygon and we're going to identify pairs of sides. And we're still going to allow translations, but now we're also going to allow dilations. So if you remember, a dilation is when you take things and you stretch them or you shrink them, and usually you do it relative to a point. So that means we can't rotate anything, and we can't reflect still, okay? But we can still get some really weird surfaces. So, here you have this surface right here with C is translated over to C and D is translated over to D. But A is dilated down to A over here, and B is dilated up to B over here. So they get stretched or shrunk. And if you go in through the bottom of A, then you'll come out through the bottom of the other A, but you're kind of going to be in a different position than you'd expect. So what's going to happen when we do something like this? We're going to get a surface that still has no local curvature, right? So it's still coming from a flat piece of paper, but it has something called non-trivial holonomy. So what's this word holonomy mean? It means that when you go around a loop, distances are going to change. So holonomy more generally can mean like if you go around a loop, then directions will change or speeds will change or things like that. But in our case, because we're not rotating and we're not reflecting, holonomy is just going to mean that distances between things are going to change as you go around a loop. Okay? So what does a picture of this look like? Well, if you and I start on the left side right here, and we start walking parallel to one another, and we walk until we get through side A and we come out, and all of a sudden we're going to find that we're closer together than we were before, which is really, really strange. So these surfaces are kind of weird to think about and get your head around. That you and I can walk in parallel lines to one another and come out and end up closer than we were before. But this is kind of the name of the game with dilation surfaces. This is what this dilation behavior adds, this non-trivial holonomy. So just like with translation surfaces, we can start asking questions about the dynamics on dilation surfaces. So what we're going to talk about first right here is the dynamics of one of these double chamber surfaces. So a double chamber surface is when you have this kind of shape here with two square pieces, and we have these identifications. And we actually had a surface similar to this when we talked about translation surfaces. It was another octagon. It also kind of had this shape, except maybe it was a little bit more crooked. But here, this is a dilation surface because we're dilating two of these sides. And when we fold this up, just like with the other surface, we're still going to get a genus 2 surface, so we're still going to get two holes. But the difference is that it's going to be folded up in kind of a weird way with things being stretched or shrunk into each other. So it's going to be a very straight surface. But you can imagine this is just like a chain link, a genus 2 surface. Okay. And what happens when we start moving around? There's still a natural straight line flow. That's because we still don't have any curvature, so our surface is still going to be, it still makes sense to move on a straight line on our surface. But the dynamics are very, very different now that we've added the dilations. So, for example, let's take a look at this flow. You start at this point, and you start moving in a direction, and what are you going to find? Well, you start moving, and then you hit the red side. But when you hit the red side is dilated, so you come out lower than you were before. Okay? So you come out kind of squeezed down a little bit, and you move over and over again. You're still moving in the same direction. You hit the red side again, and now you're going to come out even lower. Now, important to notice here is that here we hit the red side a certain distance below where we hit it the first time, right? So when we come out, that distance has to be squeezed by the factor of dilation, right? So down here, that distance got squeezed down. And then we hit the red side again, and that distance is going to get squeezed down again. And we keep squeezing that distance down by a constant factor each time, okay? So this is exponential decay, or a geometric series, if you think about it that way. And if we do this, we're going to keep going and squeezing and squeezing, and kind of like in Zeno's paradox, we're going to squeeze down so far that we actually are attracted, we're kind of converging to this green line right here. So as time goes on, we're not going to go all the way down. We're just going to slowly eke down to this green line. We're never quite going to hit it. Okay. So this is what's going to happen. And what's the deal with this green line? Well, it's actually a periodic flow. And we call it a periodic orbit because it kind of keeps going around to itself over and over again. Okay. So if you start at some point in this green line and you start moving, you'll see that it actually ends up hitting the red side right at its midpoint. So this is the middle of the red side, and so it's going to come out the middle of the other red side. Okay, but that means that it's going to keep going on its path over and over again, because if it goes in the middle of one side, it comes out the middle of the other, and then they're connected. It's a periodic orbit. It's going to keep going around on that trajectory. Okay. So this is what happens. We found a flow that actually converges to a periodic orbit. It's not periodic itself, and it also isn't dense because it doesn't go everywhere on the surface, right? So this is weird. It's very new behavior. So we've already seen that dilation surfaces can have some pretty weird behavior, and we're not really sure what's going on here, So what we should do is we should try to think about a simple example of what a dilation surface is like. Um, so let's take our analysis for the translation torus, and let's think about an analog for the case of dilation surfaces. And this is why we're going to think about the dynamics of dilation tori. Okay. So what do I mean when I say a dilation torus? So this is kind of a simple class, a simple collection of dilation surfaces. And each dilation torus has one piece of boundary. Okay. So I'll say what that means in a sec. And it means it has one cone point. So all these points are going to fold together into one point. That point is going to have angle 3 pi. And if you fold everything together, you're going to get kind of a torus like this, but it's going to have a hole in it. And that hole right there corresponds to the black side. Okay. So this is what the boundary is. It's kind of a missing piece of our surface. And the only reason we have this boundary is, you could imagine that there's more surface off to the left beyond this boundary to the bottom left. But, we want to kind of just think about what happens if our flow is in this part of the surface. So we're going to pretend it just never hits the boundary, okay? So we're only going to think about flows that go away from the boundary, not flows that go into it. And let's think about the dynamics of a dilation torus. So we can think about the straight line flow, which is moving in any direction that points away from the boundary, and we'll find the following theorem. Okay, so here's the theorem. It says that if you have a dilation torus and it has a single boundary like this, so we have any dilation torus, then the straight line flow in almost any direction is going to converge to a periodic orbit. So remember that we saw with a dilation surface that we could converge to a periodic orbit as time goes on, and it turns out that's what happens in almost every case on the dilation torus. Okay. So for example, start moving in this green direction right here, and you'll see that eventually you're going to kind of collect down to this line. And you can check that that line that you're converging to is actually a periodic orbit. It matches a point on the red side to a point on the red side on the bottom, which already are getting identified with one another. Okay. And if you take this vertical flow right here, you'll go up and you'll move up and you'll keep going like this, and eventually you'll kind of converge to this line connecting these two vertices. Now that's not quite a periodic orbit because when we hit the vertices we kind of stop, but it's called a saddle connection and it's very similar to a periodic orbit. And as it turns out, any direction in this interval, so any angle at all that you choose in this interval, if you move in that direction, you're going to converge to a periodic orbit as time goes on. So this is kind of different from what we had on the torus. Remember on the torus that we said almost every flow is dense, but when we said almost every, what we meant was the irrational flows. But if you take any two irrational numbers, there's going to be a rational number in between them because the rational numbers are dense. So in that case, we wouldn't have had any intervals like this where we run into our typical behavior for every point in that interval. So in this case, we did get an interval like that. And what happens is actually a lot weirder. So instead of getting something like the rational numbers as our leftover flows, the remaining directions that aren't going to converge to a periodic orbit are going to form a Cantor set. So this is really weird. If you remember what a Cantor set is, it's a kind of fractal. So where in the hell is a fractal coming out of here? How did we get a fractal out of nowhere? So let's try to see why that happens. Okay. And I'll remind you a picture of what the Cantor set looks like too very soon. So what does the proof for a theorem look like this? What does the proof for a theorem like this look like? It is going to look very similar to the proof that we did for the irrationality or for the irrational flows in the torus. Okay. So we're going to take a diagonal line that cuts across our dilation torus, which is going to be similar to that vertical line that we took on our translation torus. And what we're going to do is we're going to consider every time that our flow hits that line. So we're actually going to consider the induced map on this line, or the first return map on this line. So you start somewhere on the line, and then you flow until you hit the line again, and then you flow until you hit the line again, and we define a function based on this. And we can represent this function as something called an affine interval exchange transformation. So this is an affine interval exchange transformation. It's just a function that takes your interval, breaks it into pieces, reorganizes them, stretches them and shrinks them, and puts them all back together. Okay? So that's what's happening here. We take this A interval of points that go into side A and the B interval of points that go into side B, and we kind of take the A points and they go over here to the right, and the B points go over here to the left, but not quite all the way to the left because of the boundary, and we kind of reassemble them. Okay? So we get a function that looks like this. You start with A and B, and then if you're on B, you move over to TB, and if you're on A, you move down to TA. Okay? And then if we want to apply the map again, we just take wherever you landed here, move it back here, and then we apply, you kind of get shoved by B down or by A down again. And what we can do with these functions is we can understand them and manipulate them a lot more cleanly. Okay, so for example here, what we can do is we can kind of chop off this hanging bit right here of A. And what this says is, okay, don't think about points that started here, because after we map one time, we're just going to be on the right side anyway, and we don't really care what happened. We're never going to end up back here anyway, so we may as well not think about it to begin with, right? Okay, so when we chop that bit off, we're going to have to chop off the corresponding bit on the bottom. So we're going to get a map that looks like this. A goes down to TA, and B goes down to TB. And we have this gap in the middle. So these are the kinds of maps that we're interested in studying. And what's going to be really, really important here is this breakpoint. Okay, so as the direction of the flow changes, as we shift the direction of the flow, that breakpoint is just going to slide across the interval here. Right? So it's going to change the position of the breakpoint, which will change everything, but that's what's important. Okay, so how do we actually analyze these maps? Well, we're going to use something called Rosie induction to move the breakpoint around. So the breakpoint might start here, but what we can do is we can kind of chop our map off again, just like we did before. And what's going to happen when we do that? Well, we had stuff in A, which went down to here. But if we chopped off this right part, the stuff which went down which went down to the right part of A, well, we're going to have to kind of move it along to see where it goes in what's left over. So it goes up to B, and then B goes down to here. So, that stuff that was on the right part of A is now actually going to go down to B. And the stuff that was on the left part of A, well, it can just go back down to A. So when we do this kind of step of chopping off, we're going to get a new AIT that looks like this, with A over here, B over here, B over here, and A over here. So we've changed our AIT. And this Rosie induction scheme, where you just kind of chop off pieces on the left or on the right, you can imagine if the breakpoint were on the left, we would chop off the piece on the left. It lets us move the breakpoint around. Okay? And every time we do this, we can make sure that we can also revert the procedure. And as long as we can revert the procedure, if we find something out about the map at the end, then we can find something out about the map at the beginning. But if we know something about the map at the beginning, well, the flow is just a bunch of line segments connecting points from the map. So we actually find something out about the flow on the dilation torus. Okay, so the goal of Rosie induction is going to be to move that breakpoint over the gap. And why is that? Well, if we ever get the breakpoint over the gap, we do one more Rosie induction, we cut off that bit, and we end up with a map that looks like this on the bottom right. And what happens now? If you start with any point here, it brings you down to the left here, and then you go back up, and now you're just an A, okay? And now when you map down to A over here, you're just an A again. And you keep going, and you keep kind of shrinking down until you get to a single point in A. And that point just keeps going back to itself over and over and over again. So we are converging to a periodic orbit. Okay, but if we converge to a periodic orbit here, then we can go back up one induction and we'll see that we converge to a periodic orbit there. And we can go back up another induction, we'll see we converge to a periodic orbit there. And you can keep carrying this up and up until you lift all the way back to the dilation surface. And you'll find that your flow converges to a periodic orbit. Okay, so we found that if your Rosie induction moves you over a breakpoint, moves your breakpoint over the gap, then you have a periodic orbit. So when does that happen? Well, you can imagine if we nudge this breakpoint to the left or to the right, we still stay over this gap. So there's an interval of breakpoints which start over the gap, right? Or if we have Rosie induction, where we do a right Rosie induction, and we have this breakpoint here, if we move it to the right or to the left, we do another right Rosie induction, we'll still be over the gap afterwards, okay? So let's take the interval of all possible breakpoints, and let's mark down the places where it's over a gap after no inductions, after one left induction, after one right induction, after two left inductions, after one left and one right, after one right and one left, and after two rights, and etc., etc. So this is what we're going to get. The red interval here corresponds to breakpoints over the gap. The red interval HL corresponds to breakpoints which move over the gap after one left induction. HR corresponds to breakpoints that move over the gap after one right induction, and so on, left, 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 right, right, left, and right, right. And they keep kind of taking up the spots that were left over by the rest of the intervals. But this is exactly the construction of Cantor's middle thirds fractal. We start with an interval and we remove the middle of that interval, and then we remove the middle of what's left over, and we keep removing and removing, and we find that what's left at the end is a Cantor set. It's a fractal that looks kind of like this. So if we keep removing these intervals where we converge to periodic orbits, we'll get the things that don't converge to periodic orbits, and they're going to be a Cantor set. And you can actually show that every time you're removing about a constant proportion from each interval, and that means that the resulting Cantor set will have length 0, which you can translate back to saying that almost every direction will have a converging to a periodic orbit, and the leftover directions, well, first of all, they'll happen with probability 0, so almost none of them will happen, and they'll almost never happen. And they also, those directions are going to look like this. They're going to look like a Cantor set. So, maybe you could imagine those directions kind of wrapped around a circle, that Cantor set wrapped around a circle where it would correspond to angles. So that's what the proof looks like. The really crazy thing happens when we ask the question, what happens to those directions? So we have all these directions here, and we want to know what happens in those directions too. I mean, we know in the other directions that we're going to converge to a periodic orbit, but what's going to happen if you move in one of these Cantor set directions? The crazy thing is that they themselves will converge to Cantor sets. And this is a totally unrelated Cantor set. It comes out of seemingly nowhere. Why are these flows converging to Cantor sets? It's really, really weird, and it's kind of hard to understand what's going on there. So let's talk about the theorem. The theorem says that if you take a direction in the Cantor set of all directions that do not converge to a periodic orbit, then, except for in a couple exception cases, that flow in that direction is going to accumulate to a set whose cross-section is a measure 0 Cantor set. So what do I mean by that? I mean that if you flow in this direction, you're going to kind of accumulate onto all these lines. And if you cut across those lines, what you're going to get is a Cantor set. Okay? So this is kind of like a lengthened Cantor set that we are converging to as time goes on. This is what your flow does, and this fractal just kind of pops up out of nowhere. And the crazy thing is it's a totally unrelated Cantor set to the Cantor set of directions. So remember, we had a Cantor set of directions. This is a Cantor set on the surface that we're converging to as time goes on. Okay. And how do you prove something like this? You do some nasty topological argument, which is not super interesting, but it's a crazy fact that this happens. And so two really cool researchers, Bowman and Sanderson, who did some research on this topic, made a really, really cool plot of what happens if you think about what these Cantor sets look like. So what they did was they took the flow moving in any direction. So they looked at, as you change the direction, what happens if you cut across the flow and look at just what the cross section is of wherever that flow converges to. Okay, so usually it's just going to be a periodic orbit, and so when you take that cross section, it's just going to be a finitely many points where you're passing through over and over again, but you just keep repeating. Okay, but then when you get these Cantor sets, you're going to get a Cantor set intersection. So what happens when we plot this? we get this really, really cool diagram. So on the bottom here is represented the angle. It's parameterized between 0 and 1, but you can imagine it's just the angle between like 0 and 180 degrees. You move on the surface. And on the vertical axis, we have the cross section of a diagonal. So, you can kind of see here if you looked at the angle 0.4, say, and you took this slice that goes up here, you would see what the flow looks like, how it intersects a diagonal. Okay? And you can see that this sort of picture here has really complicated behavior. So it's not too surprising now that a Cantor set is coming out of this. But in fact, we kind of have two Cantor sets, right? Because there's a Cantor set of angles where if you take the cross sections of those angles, then you also get a Cantor set on the vertical axis. So it is kind of a crazy plot. So this is the sort of thing that you can find in just this really, really, really simple surface, the dilation torus. And that's kind of scary, because if dilation surfaces have such rich dynamical behavior, then who's to say that I guess what I should say is if a dilation torus has such rich dynamical behavior, then who's to say that dilation surfaces don't have crazy exotic behavior that we could never possibly get a grasp on? Okay, so we've seen that dilation surfaces have crazy new dynamical behaviors, but what we do know is that for the translation surfaces, the torus is very representative of the dynamics on a general translation surface. That's what the Kirchhoff-Maser-Smiley theorem says. So then the question becomes, is it also true that dilation tori are representative of the dynamics on a general dilation surface? We might wonder, is it true that on any dilation surface that almost every flow converges to a periodic orbit? And this is actually the big conjecture, that if you take any dilation surface at all, if it's not a translation surface, so as long as it has some dilation, then the straight line flow in almost any direction is going to converge to some periodic orbit as time goes on. Okay, so this would be like the analog to this theorem, which says that in almost any direction, you converge to a periodic orbit. But even if you were to prove something like this, you still wouldn't have any clue what happens on leftover directions. Okay? So this is kind of a great conjecture to have, but it shows just how little that we know about how dilation surfaces could possibly work. Now, how would you prove a conjecture like this? Well, you might have to do something similar to the Kirchhoff-Maser-Smiley theorem, where you consider the dilation or the moduli space of all dilation surfaces, and then you do a flow on that moduli space and you find an invariant measure, and that tells you something about the result. But people are working on this and it's not yielding any information. I mean, it's just really, really hard to do. So maybe there are other methods you could try similar to the one that we did for the dilation torus. But right now this seems like kind of a hopeless conjecture. But a lot of people are working on it and we'll see what happens. In any case, thank you very much for listening to my talk. And yeah, I appreciate you taking the time to listen to a recording, even if you weren't able to make it to the live talk.